Another problem on pumps. So this person has a garden and then he wants to water his garden easily. Now he has enough water, but the water doesn't flow as expected. So it's just natural drafts, which is not enough to garden or to water a big garden. So you can calculate the loss using the module 4. What we have learned in module 4, you can calculate the loss in valves and pipes and assume that that is 15 psi loss, and then you want about 25 psi at the tip of the water hose, so it gets a little bit easier to water the plants. Now also you want some flow, not like very small pump, so about 50 gallon per minute flow, and assume that it runs on 1000 rpm coupled with a 1000 rpm motor. Now here is the questions. What is the minimum psi rating? So total pressure, you got about 15 psi loss in the system, plus you need 25 psi available at the tip of the garden hose, so which is about 40 psi. So that's question number 1. And then next question is, how much power do you need for this pump? So we know that P equal to power equal to pressure in psi, if we have this in psi, and then Q is in gallon per minute, then you divide by 1714 to get the horsepower. So let's have all this number plug here, that, and then the pump was 50 gallon per minute capacity pump, divided by 1714, which is about 1.16 horsepower. I calculated output power. Now what's the if the overall efficiency is 85%, what's the power rating of the pump? So overall efficiency is the power output by power input. So 0.85 is equal to, we want 1.16 horsepower output. So what would be the input power? Now P power is in caps lock and P pressure is in a small letter, so just make sure you have the distinction for that. So that's the horsepower you need for the pump. Now typically it is difficult to find a pump that is 1.37 horsepower, so instead it's just wrong, it should be in B, C. So you buy a pump that is about 0.5, so maybe the power between half horse to 3/4. You can also find pump at this range horsepower, or maybe even 2 horsepower, depending on which one is more available and cheaper. Now the theoretical flow rate, which is QT, is the VD times N. What's that? What's the calculate the pump theoretical flow? It's just asking for theoretical flow. We can use this way to calculate the theoretical flow, but we don't have this piece information available. We don't have VD. So let's use the volumetric efficiency to calculate the mechanical efficiency first, and then we can calculate the theoretical flow. Do you have the displacement? Let me just pause. So we haven't still calculated that VD, so we cannot really use this equation VD times N. On the other hand, we can use this volumetric efficiency equation. So volumetric efficiency is the theoretical flow that the power pump should develop, and the actual flow after the slippage. So actual will be less than the theoretical flow. Now so 0.9 is equal to QA, which is 50 gallon per minute, divided by QT. So QT is equal to, I calculated 55.55 gallon per minute. That's the theoretical flow. Now volumetric displacement. Now we know the theoretical flow. So theoretical flow QT is equal to the volumetric displacement, which is in rev per minute, the unit for that, and then the RPM, which is rev per minute. Sorry about that, this one should be inch cube per rev. That's the unit. So let's plug all this number. I got 55.55 gallon per minute. I'll convert that to inch cube because displacement is a smaller unit, so it is expressed in inch cube. I know that 1 gallon is 231 inch cube is equal to VD will be in inch cube per rev because we converted already in inch cube, and then the RPM is 1000 RPM rev per minute. So let's use this space. So if we solve for VD, it's gonna be, I calculated 12.83 inch cube per rev, or typically that per rev is silent for displacement. Mechanical efficiency, we know that the overall efficiency is equal to mechanical efficiency times the volumetric efficiency. So we know that overall efficiency was 0.85. So mechanical times the volumetric efficiency was given 0.9. So mechanical efficiency would be 94.4%. That's what I got in my calculation. Theoretical torque developed by the pump. We can use this equation. Theoretical torque is VD. We can actually calculate this in couple of ways. One of these is the VD times pressure divided by 2 pi. We just calculated VD, which is 12.83 inch cube times pressure was 40 psi divided by the 2 pi, which is equal to 6.8 pound-feet of torque. Like that. Now calculate the actual torque developed by the pump. It should be actually actual torque needed to drive this pump. Actual torque needed to drive the pump. That's what the language should be. So N mechanical efficiency is equal to theoretical torque that you have calculated to drive the pump. However, actually it will take more. So smaller divided by more, that's the efficiency. So basically I have calculated TA, the theoretical torque 6.8 pound-feet, and then divide by 0.949, which is equal to 7.21 pound-foot. I think that's all the question developed for this problem.